Dear friends, here we are. I have to tell you what specifications I gave to the industry 10 or 15 years ago. What specificities should a vitrectomy machine have and for what reasons? You will see that it is much simpler than what is currently proposed to you, when the goal is only to meet needs and not to differentiate from competitors by proposing more and more complicated things. And we know that complexity increases the risk of failure. What is needed? There is a need at all times to precise control the amount of fluid entering the vitrectomy, the phaco or the posterior phaco handpiece. To precisely control the vitrectomy cutting frequency and ultrasound efficiency, and to precisely control the power of the dithermy. We need a BSS infusion system to compensate for the aspirated fluids and maintain the desired IOP, and a system for injection and extraction of silicone or other fluids. We need a low toxicity lighting system and, if possible, a laser and a cryo whose control could be managed with the same foot pedal to avoid having to play on several pedals like an organist. Finally, we need a computer control system that allows us to customize programs for each operator. I believe that each of us would sign these specifications without restrictions, but let's see now in detail, point by point, what it means. It may seem obvious to say that the only way to precisely control the amount of fluid entering the handpiece is to use an aspiration flow control pump. This is to say, a volumetric pump. The volumetric pump, by moving part of the internal volume of the aspiration tubing downstream, will create a virtual space that will be filled by the same volume of fluid upstream, whatever its viscosity. And this is how the fluid column will progress. By expelling 1 cubic millimeter of fluid downstream, it will automatically suck 1 cubic millimeter of fluid upstream. If you choose an aspiration flow rate of 2 cc per minute, regardless of the viscosity of the fluid being sucked in, the fluid column will advance at a rate of 2 cc per minute in a regular and continuous manner. With a non-volumetric pump, such as the Venturi pump, you will create a depression downstream at the distal part of the tubing, a pressure lower than atmospheric pressure. This vacuum will increase the pressure gradient, the pressure difference between the pump and the intraocular pressure, and will therefore cause the fluid column to move forward, but not in a controlled and regular manner. For the same vacuum, for the same depression selected at the foot pedal, there will not be the same quantity of fluid entering the handpiece, and this suction rate will be all the more unpredictable, as it will depend on the viscosity of the fluid at the handpiece level, but also at the level of the entire aspiration tubing. This is perfectly demonstrated in this video by Keith Warren, who shows 2 syringes, each containing 10 cc of air, 10 cc of water, and 10 cc of honey, so 30 cc. The one on the left is connected to a Venturi pump set at minus 300 millimeters of mercury. The one on the right to a peristaltic pump set at 15 cc's per minute, which is designed to pump the syringe in 2 minutes. The difference in behavior is clearly visible. At the beginning, the two pumps will suck the honey at about the same speed in about 40 seconds. Then, on the left side, when the venturi pump will pass through the water, the speed of aspiration accelerates and becomes uncontrollable in the air. On the contrary, on the right, the peristaltic pump will continue to regularly suck at the same speed in the water and even in the air, which explains why it is so precious in fluid air and especially air-fluid exchanges. What difference does it make on a practical level? First of all, for central vitrectomy at the beginning, when far from the retina, the operator working in flow control will be able to use higher flow rate close to the maximum infusion flow rate, since he knows that even when it is in the BSS, the flow rate will be the same. It will not increase or exceed the infusion flow rate. In venturi, if the operator chooses a high vacuum, equivalent to the vacuum used by the volumetric machine to obtain this high flow rate, when he moves from the vitreous to the BSS, the flow will reach too high levels. And the odd thing is that I often hear the opposite. Some operators start their central vitrectomy with a venturi because they think it's more efficient. They don't understand the flow control setting. The flow control pumps are faster because they allow you to use vacuum levels that would be dangerous with a venturi. And they even allow an increase in vacuum faster than a venturi pump. This has been proved. And it's easy to understand. If you pull on a plunger of a syringe, which is a volumetric pump, you're going to create a high vacuum immediately, faster than a vaporizer does by flowing on a hose. When it has done this central vitrectomy and gets closer to the peripheral vitreous, the operator using a flow control will decrease his flow rate to allow him to control the vitreous, which will enter the NP slowly, regularly, and continuously. For example, he can choose a flow rate of 4 cc's per minute and can cut slowly or quickly. It's up to him. He will decide. There is no risk of unpleasant surprises. Whether it is on BSS or in vitreous, the speed of a fluid entering his handpiece will be the same at 4 cc's per minute, and he will control it. If he works with a venturi pump, he has to have the same flow rate of 4 cc's per minute in the BSS. He must not exceed minus 40 millimeters of mercury in 23 gauge and minus 90 millimeters of mercury in 25 gauge. And he will never work with this vacuum level. Why not? Because once he has drawn the vitreous into his handpiece, the friction will bring the flow rate down to less than 1 cc per minute, and he will find that it is not efficient enough. He will then choose a vacuum of minus 200 or minus 250 to have an acceptable flow in the vitreous. But he will then have a too high aspiration flow in the BSS in the order of 8 to 11 cc's per minute, which will attract the vitreous in an uncontrollable way, because you must understand that it is the BSS that is sucked in that makes the vitreous come into the NP port. And this is exactly the accident that happened to me and that I shown in the previous chapter, when in a third of a second I bit the retina. With a venturi pump, the handpiece then becomes dangerous because it does not allow to control the progression of the vitreous as the volumetric pump. The operator cannot choose his cutting frequency anymore. He will be forced to opt for high-speed cutting, even if this goes against all his everyday gestures. Because high-speed cutting is nothing more than a way to reduce the dangerousness of the handpiece. On the other hand, it has disadvantages that we will see later on. It is terrible to be afraid of your handpiece because it is your tool. It must be your friend. It is there to help you to work the way you want to work, not to create damages or impose behaviors on you. Finally, the operator will tackle the most precise work to remove the adherent posterior haloid and the last small vitreous adherent fibers at the vitreous base. If he uses a flow control machine, he will select flow rates of half a cc, 1 cc, or even 1.5 cc with a foot pedal to safely engage the posterior haloid for peeling, or to engage at the base the small vitreous adherent fibers before cutting them flush with the retina. If at that moment the pressure at pump level is measured, this pressure is positive, higher than atmospheric pressure. How can this be explained? Well, in fact, the simple IOP creates a pressure gradient responsible for a natural flow rate that would cause the BSS to flow out at the end of the aspiration tubing if the tubing was pulled out of the pump. The volumetric pump can slow down this outflow by allowing less BSS to pass through that is generated by the IOP. It's like a dam that lets less water through than the flow of the river. If we measure the pressure exerted by the water at the outlet gate, the pressure is very positive. It is the same here. And that's why this work is not possible with a venturi pump, because by definition, a venturi pump can only exert a depression lower than atmospheric pressure. It can only increase the pressure gradient between the eye and the atmosphere, and cannot work in positive pressure. In 23G, it will be impossible to work at less than 3 cc's per minute. And if we want to do the same precise work, it will create accidents. This is why here too we have no choice but to work with high-speed cutting. A low-flow operator can decide to do a peeling, and if he does not succeed to do it, to make a shaving, which will not protect as much the patient from the post-op PVR. But a venturi operator can only do a shaving because he suffers from the danger of the machine, which forces him to work in high-speed cutting. Therefore, he has to adopt a particular behavior. And this is also demonstrated in the EV-SRD study, where a multiple correspondence study was able to individualize two groups of operator behaviors according to whether they were using a machine equipped with a venturi pump or a volumetric pump. Venturi users preferentially use high-speed cutting, install more 360 encircling backing because they leave more anterior vitreous, and inject more siliconoid to prevent the greater risk of post-op PVR. So, why not? We have the right to be a little more aggressive. This would not be serious if these behaviors imposed by the dangerousness of the Venturi pump did not end up with 3 times more lost eyes, and this is indisputable and highly significant, p equals 0.006. And we are not talking about eyes where the silicone cannot be removed. Therefore, it is necessary to opt for a machine equipped with a volumetric pump. So, what kind of volumetric pump? Piston pump, membrane pump, eccentric water pump, peristaltic pump. There are different types of volumetric pump. If I had to recommend a type of pump, I would choose the one that presents the least risk of failure. The advantage of the peristaltic pump is that it is extremely reliable. A simple rotary motor, such as the Viper motor, turn the rollers and that's it. A Viper motor never fails. The only precaution one must take is to put enough rollers, or better, to place them in phase opposition so as not to have the pulsatile character of the peristaltic pump of the 80s. The second advantage is that a motor like this can fit in 1 cubic centimeter, and that it is therefore very easy to imagine that the pump system could be placed in the handpiece, which would have 2 advantages. On one hand, the pump would always be at the eye level with the patient, thus increasing the reliability of his action. On the other hand, there would be upstream to the pump only the non-deformable metal part of the handpiece. There would therefore be no compliance forces due to the elasticity of the tubing or micro bubbles. If the motor makes the rollers rotate a 4th turn, either forward or backwards, the fluidic repercussion at the port level will be in directly engagement and therefore excessively precise. The third advantage of the peristaltic pump is that we all understand how it works, since we have the same pump system in our body at the level of our intestines. And we can easily imagine the catastrophes that a tourista would cause if a Venturi pump replaces our peristaltic pump. Let's now move on to the control of the cutting frequency. But first of all, let's see how the vitreous is cut. The problem is that the vitreous is not a Newtonian fluid like water, BSS, honey, or oil. If you apply even a tiny depression on the Newtonian fluids, it will move. But the vitreous is a non-Newtonian fluid. Those cohesive and elastic fibrillar properties allow it to move only by deforming. We are well aware of these cohesive and elastic components when we have to manage a vitreous exit. The vitreous will come only into the handpiece port if the forces that attracts and deforms it is greater than the restoring force linked to its elasticity and shape memory. If this force is less than the recall force, the vitreous will not move. Let's see this in more detail using a very practical example. You immerse the handpiece in vitreous after having placed your BSS infusion. The port is in contact with the vitreous. You are aspirating. The vitreous fibers in front of the port will be sucked in by the depression. They will deform, enter the port, and drag their neighbors right behind them because of their cohesion. Then the knife cuts these fibers. The neighboring or the neighbors neighboring will go backward because of their elasticity. The small vitreal space corresponding to the aspirated and cut fibers fills up with BSS, if we exclude the force of gravity. It's too much complicated. If the handpiece does not move, the next time the door is open, it is the flow of BSS attracted by the depression that will drag the neighboring fibers into the port. For this to have time to happen, the port must be open for a time that allows the depression to attract the BSS and then the vitreous. What practical consequences this have on the cutting frequency? After finishing the central vitrectomy and the mid-periphery, you want to cut adherent vitreous by cutting it flush with a detached retina. So you are in the BSS and you want to engage the vitreous traction in the port to cut it at 1/10 of millimeter or 2/10 of millimeter from the retina. To do so, you must generate an aspiration flow of BSS whose force of attraction will be just higher than the return force of vitreous traction. This restoring force will not be the same in all cases. If the fluid under the retina is viscous, as in all detachment, it will suck the retina and the retina will exert an additional restoring force that will be added to that of the vitreous traction, and you may need a flow rate of 2 cc per minute. If the fluid under the retina is BSS, as it is the case in giant tears, you may need a flow rate of 0.5 cc per minute. This suction flow rate, which is just above the overall restoring force of the traction, can therefore only be assessed empirically on a case-by-case basis. You will need to increase the flow rate gradually to first horizontal traction, then bring it into the port before cutting it at the desired location, just like cutting a suture wire flush with the knot. This takes some time and requires either cut-by-cut basis or a cutting frequency of 1 cut per second or even 1 cut every 2 seconds. This is the minimum frequency we need. In terms of maximum frequency, what is the maximum cutting frequency required? No, we are getting into a chapter where I'm not going to make friends. For the last 10 years or so, in a kind of collective hysteria, manufacturers have been competing in ingenuity to offer a higher and higher cutting frequency. This may be understandable on the part of manufacturers of machines equipped with a venturi pump, because the high-speed cutting reduces its dangerousness. But this madness has also contaminated the manufacturers of machines equipped with volumetric pump, and theirs it's beyond comparison. Here is what I already presented more than 20 years ago.
Here I'm cutting at 600 cuts per minute. The retina moves because the adherent vitreous has the time to come in the port. Now I'm using 1,800 cuts per minute, and a miracle occurs, for the retina no longer moves, giving the operator the illusion of having finished an excellent vitrectomy. But the problem with this illusion is that the procedure is very incomplete. If one passes a needle just above the retina, one is going to pull all the adherent vitreous cortex, which has not been removed during this high-speed vitrectomy. On the contrary, with a low aspiration flow and no cutting, we are able to detach this cortex. High-speed frequency cutting permits a very secure but very incomplete vitrectomy to be carried out, since it only allows one to cut the extremities of the fibers. It's no secret that if we want to remove more adherent vitreous, we must first make it come to the port by a low cutting frequency, and thus must also cause the retina to move. Then, to avoid retinal damage, we must control the aspiration flow.
And there, it was only 1,800 cuts per minute. This is to say 30 Hertz, which means that between two cuts there is only 300ths of a second to allow the BSS to transport the vitreous by deforming it. So imagine what happened at 9,000 cuts a minute. It is true that the vitreous adherent to the retina, not coming in the port, the retina does not move and gives the impression to the surgeon that he is very skillful. But the purpose of a machine is not to flatter the ego of the surgeon. It is to allow him to remove all the vitreous. What happens when the frequency is more than 2,000 or 3,000 cuts per minute? In 200ths of a second, the BSS does not have the time to attract the vitreous, and the only thing that goes into the port is the BSS. This was shown very clearly by Philip Koch with a high-speed camera. Around the port, a volume of BSS is formed, and the vitreous around this volume does not move. This is why the manufacturers say that the flow rate increases when using a venturi with a high-speed frequency, because only BSS is sucks and without any friction force. We can see it clearly here on this example where in 23 gauge at 8,000 cuts per minute, the pump remains in positive pressure between plus 20 and plus 30 millimeters of mercury, simply because no vitreous is sucked in. Proof can be given in this example where, as long as I cut at high speed, the hemorrhagic vitreous at the base does not come into the port, and as soon the frequency drops, it rushes in. At high speed, the only way to aspirate vitreous is to plunge the port in the middle of the vitreous, as we saw earlier. And if we move the handpiece, we will make a line in the vitreous with a width of a port diameter. I experienced the same feeling when I tried a cutting probe with Susan Binder about 20 years ago, where the cut was performed by an holmium laser produced by Wavelight. I felt like I was in a room full of smoke and I had a lightsaber like in Star Wars that actually only remove a small sprinkle of smoke, and no matter how much I shake it, nothing or almost nothing moved. Here the surface of the door is a tenth of square millimeter, and we have to remove 4,000 cubic millimeter. So imagine, if you take time, you can do it, but what a lack of efficiency. The last thing I will criticize is this system where the knife coming down does not close the port. It is a blade cutting in both sides, narrow enough to clear behind it an aspiration space when it reaches the end of its stroke. The purpose of this system is twofold. Firstly, as the blade cuts both ways, it doubles the cutting frequency. And secondly, as the door is always open, the aspiration time is increased and maybe slightly the higher maximum aspiration flow rate. This system is proposed by the American companies, but also by Dork, who, although having a very good volumetric pump, wants to participate in this race to whether will be the fastest. The problem is that this type of cutting modifies the dynamic of the vitreous. Let me explain you. When the BSS flow has attracted and deformed the vitreous to bring it into the port, at the moment when the knife is going to cut the fibers, neighboring fiber will be sucked by the upper door behind the knife, and when these neighboring fibers are cut, the lower port will be open and active again. The vitreous will therefore not have time to go back under the effect of its elasticity. Everything will happen as two hands can do it, each one pulling in turn on an elastic band without letting the elastic band go backwards. This is dangerous because a high-speed cutting can bring the retina to the door, to the port, in a tenth of a second. Here is an example where, although cutting at 4,000 cuts per minute with a flow rate of 3 cc's per minute and a vacuum around 10 millimeters of mercury, therefore extremely safe parameters that normally do not allow the retina to move, the TDC system caused me to get a retinal bite. Let's avoid these systems. There is no need to double the frequency, since the maximum useful frequency with a flow control pump will be around 2,000 cuts per minute. So, to summarize this chapter, the ideal machine should allow us to control the aspiration flow rate from 0 to 15 cc's per minute with a spatial precision between 0 and 2 cc's per minute. The cutting frequency from 0 to 2,000 or 2,500 cuts per minute with a spatial precision in low frequency, allowing a frequency of 1 per second or 1 every 2 seconds. Here it is. We will see in the next chapter the other characteristic that the ideal vitrectomy machine must offer. See you soon.